All right, everyone, welcome to what will likely be the first part of two parts for this video lecture for Chapter 3. Chapter 3 is all about the properties of water. Obviously, we know that water is very important for life on Earth. If you think about NASA, for example, when they send, spaceships, probes, and things to Mars or other moons in the solar system, they're looking for life primarily. That's one of their key missions. But when you think about it, do they really look for life directly in most cases? Do they have a camera looking around for little green men, that kind of thing? Probably not. What they're really looking for is water. And the reason why they're looking for water is because we know, at least from our experience here on planet Earth, that if there's no water on a planet or a moon in our solar system, no liquid water, then the chances for life are practically zero. So clearly water then has some very important properties and very important role to play in our biology. It makes our biology possible, okay? So water is referred to as the biological medium here on planet Earth. It's the only common substance to exist in the natural environment in all three physical states of matter, so solid, liquid, and gas, and it can do so over a fairly narrow temperature range. Now, as we're going to see in this chapter, the majority of these properties of water that make it so good at supporting life are a result of the structure of the water molecule. So we're going to get back into this idea that we hit on a little bit in chapter 2 of structure and function. Again, things work the way that they do or have the properties that they do because of their structure. The structure gives the function, okay? And it's certainly true with water. Now, these properties that we have in water that make it so good at supporting life are referred to as emergent properties, okay? Emergent properties. Again, you take the things that water is made of, right? 2 atoms of hydrogen, 1 of oxygen, and separately by themselves, they have very specific properties. As an example, hydrogen and oxygen are both very combustible, very explosive. Separately, you put a spark to them and they both explode. Now, put them together in a ratio of 2 hydrogens to 1 oxygen, and you've got water, which puts out fire and will not explode. So those new properties of water that hydrogen and oxygen by themselves don't have are examples of emergent properties. They're properties that emerge as we take simple things and build them into more complex structures. So the point here is that water has some very unique emergent properties that make the planet suitable for life. So take a look at planet Earth and you see this beautiful blue sort of marble floating there in outer space. The reason for all that blue is water. Now, the vast majority of the blue that you see there is obviously the oceans, right? So it's salt water. Salt water makes up about 97.5% of the water that's on the planet. So the remaining 2.5% is fresh water, water in rivers and lakes, wetlands, that sort of thing. And actually, the majority of that 2.5% of fresh water is tied up in the polar ice caps. So very little of the water on the planet is actually fresh, okay? All right, so water is a very important commodity, obviously. So what is it then about the structure of the water molecule that gives it many of its life-supporting properties? Well, if you recall, in the last chapter, I showed you the basic structure of the water molecule, right? H2O. You have these 2 hydrogens covalently bonded to the 2 oxygen, or to the 1 oxygen rather. And remember, there are 2 lone pair electrons around the oxygen that then sort of force those hydrogens sort of down at this angle like this. So water has that sort of odd shape that you see there. It's about 105 or 109 degrees, something like that between these two, rather than 180. They're not directly across from each other. In addition, these covalent bonds here are polar covalent, okay? Polar covalent bonds, meaning that the pair of electrons being shared in this bond are being pulled toward the oxygen because, again, oxygen is electronegative, and that electronegativity of the oxygen pulling negative charge or negatively charged electrons toward itself gives this side of the water molecule a slight negative charge and leaving a slight positive from the protons and those hydrogens on the opposite side. So water is also called a polar molecule. If it weren't polar, we wouldn't care because we wouldn't be here talking about it. Water would not support life if it were not a polar molecule. So that special feature of oxygen being electronegative is why water is polar, and water being polar is largely why it supports life, as we're going to see. Okay, so let's take a look at this animation here that explains some of this.
The atoms that make up a water molecule are in a constant tug-of-war over their shared electrons. Oxygen exerts a far stronger pull on the shared electrons than does hydrogen, and so the electrons spend more of their time closer to the oxygen atom. Because of this unequal sharing of electrons, the oxygen atom in a water molecule actually has a slight negative charge, and each hydrogen atom has a slight positive charge, even though the water molecule as a whole is neutral. Because of the unequal sharing of electrons and the resulting positive and negative poles, a water molecule is said to be polar. The polarity of water molecules causes them to be attracted to each other. Since the positively charged atom involved in this special type of attraction is always a hydrogen atom, this kind of bond between molecules is called a hydrogen bond. Each water molecule can hydrogen bond to 4 other water molecules. A hydrogen bond is weak and lasts only a tiny fraction of a second, but it takes a lot of energy to overcome the combined attraction of many hydrogen bonds. This explains water's great capacity to store heat, its high boiling point, surface tension, and several other unusual properties.
Okay, so let's go on to next slide here. All right.
The atoms...
Oops, sorry. Okay, so as the animation showed, excuse me, because of the polarity of the water molecule, every water molecule can hydrogen bond to 4 other water molecules, and that's what you see in this figure here. So let's go over the definition for a hydrogen bond once again. Remember, a hydrogen bond occurs when a hydrogen atom that is covalently bonded to one electronegative atom, like the oxygen here, is also attracted to another electronegative atom. All right. So in this case, that other electronegative atom is an oxygen and an adjacent water molecule. That's your hydrogen bond. Again, always shown as the dotted or dashed line to indicate it's weak. It's an opposite charge attraction between a hydrogen and some other electronegative atom. So the fact that these 4 water molecules, or actually 5 water molecules that you see here, are bonded to each other in this way is why water behaves the way that it does, as we're going to see here in a little bit. Okay. All right. So water is sort of recognized as having 4 sort of key emergent properties that help it to contribute to Earth's suitability for life. So what are these properties? Well, we have water's cohesive behavior. Okay. Cohesive means the water molecules sort of stick together. That's kind of what that last figure was showing you, the water molecules sticking together through hydrogen bonds. Water is also very good at moderating temperature, as we'll see. Water expands upon freezing, and it's an excellent, actually, solvent. So water has cohesive behavior, it's very good at moderating temperature, it expands upon freezing, and it's a good solvent. So these are the 4 key emergent properties of water that contribute to water making life possible on Earth. Okay, let's talk about cohesion first. So collectively, hydrogen bonds, as I showed you in that previous slide, hold water molecules together. That sticking of water molecules to each other through hydrogen bonding, that is called cohesion. All right. Now, cohesion helps the transport of water, for example, against gravity in plants. That's one way that water helps support the existence of large multicellular organisms, as we'll see. Helps to transport water against the force of gravity. So cohesion is the tendency of water molecules to stick to one another, but there's another related property that is referred to as adhesion. All right, so let me just write this in here, and adhesion. Adhesion That's an H, by the way. Adhesion is the tendency of water molecules to stick to other substances, like the insides of the water transporting tubes in plants or your blood vessels, that kind of thing. So let's take a look at this in plants. Excuse me. All right, so think about a large tree. A large tree is really nothing more than a water pump, okay? That's true really of all plants. So this tree is taking water in from the soil through its roots, pumping it up the trunk, into the branches, and into the leaves, and eventually the water leaves the surface of the leaves and goes off into the atmosphere. That's called evapotranspiration. That's one of the things that plants do. That's how water gets back primarily from the soil back into the atmosphere so it can rain again. It's an important part of what's called the hydrologic cycle, the water cycle of the planet. That's why you always see sort of a cloud of mist or vapor over the rainforest, because all of those trees are pumping water out of the soil back into the atmosphere. Now, the thing is that the tree here, is not expending any energy whatsoever to make this happen. This is happening on its own. It's due to adhesion and cohesion of water molecules. So if you were to peel back the bark of this tree and look underneath of it, there's a very, very thin tissue layer sitting between the bark and the wood of the trunk. The wood of the trunk is dead tissue. It's previously living but now dead cells. So there's a circulatory tissue underneath the bark on top of the wood, and this is an electron microscope view of that tissue, and you see these very, very small diameter tubes, okay? Those are the water conducting tubes that run in that tissue layer underneath the bark. And because they're very narrow, they transport water against the force of gravity without the plant using any energy. This works in much the same way that wicking of water up fabric does. You take a piece of fabric, you put the tip of it in water, and what do you know is going to happen? The water is going to absorb or wick up into that paper or paper towel or that cloth or whatever it is that you're putting in the water. That's due to adhesion and cohesion of water. In these tubules here, what you see is that the water molecules are going up sort of in a train-like fashion, and they're hydrogen bonded to each other. That's cohesion, right? But they also stick to the insides of the tube through adhesion. Now, if that's an oxygen, you know it's negative. There must be a positive charge here on the inside of that tube. So the inside of these tubes are sort of peppered with these positive and negative charges that water molecules can stick to. And the water molecules bounce from one to the next to the next. They bounce from one charge to the next. And so the first one's bouncing along, it's pulling the next one, which is bouncing along with it through hydrogen bonding, cohesion. Adhesion is them sticking to the walls, and they go right on up. And this is exactly how water wicks up into the fabric or a piece of paper that you put into water. But the tree here is using that to its advantage because it doesn't have to use any energy to pump that water that high as we would in a skyscraper, for example. Instead, it pumps it for free. Okay, so this also plays an important role in your circulatory system as well, helping the plasma of your blood to move through microscopic capillaries and things. Without this wicking behavior of water through adhesion and cohesion, our circulatory system would not work the way that it does. All right, so I have an animation for that. Let me show this.
How does water get from the roots of a tree to its leaves? The evaporation of water from leaves moves water molecules up from the roots. The evaporation exerts a pull that is relayed downward along a string of water molecules from leaf to root. Hydrogen bonds cause water molecules to stick together, a phenomenon called cohesion. As each water molecule evaporates, it pulls on the next water molecule, and it pulls on the next. This relays the pull of evaporating water molecules all the way down to the roots. The cohesion of water helps to keep gravity from pulling the water molecules back down.
All right, so a phenomenon that's sort of related to this is that of what's called surface tension. Okay, everyone has seen an example of surface tension in action, whether you realize it or not. Surface tension is a measure of how hard it is to break the surface of a liquid. And another key feature of water is that it has an unusually high surface tension compared to other liquids. And this is due to hydrogen bonding between the water molecules at the air-water interface and to the water below. So let's imagine, for example, that you have, say, a beaker of water here. All right, here's your beaker, and here's the fluid surface, the water surface. At depth, you have water molecules that are all sort of evenly spaced and hydrogen bonded to each other. But at the surface of that water, they can't go up anymore, so they're sort of tightly packed together. And that creates sort of a skin or a film of more compacted water on the surface. That's surface tension. It's sort of like the skin on the surface of a pudding. You punch through that to get to the pudding below, but the skin is sort of a thin layer on top of that. And that's called surface tension. Water has an unusually high surface tension. And this allows for all sorts of things. So take a look at this photo here, for example. This is why water beads up on surfaces like these blades of grass. This is why when you step out of the shower or the bathtub or a swimming pool, you've got beads of water on your skin. This is because of surface tension. So this water up here is sort of resisting the effect of gravity to sort of flatten that water bubble or water droplet rather down. This skin of water molecules on the outside is giving it high surface tension and allowing it to resist the effect of gravity. And there are actually a number of organisms that take advantage of this. The spider, for example, is adapted to take advantage of the surface tension of water to sort of walk on water. So basically what it does, you see how the tips of the feet, the legs are actually making these little dimples or depressions. They're not punching through the surface of the water. They kind of act like snowshoes, really. These the feet of the spider, the undersurface has what are called non-wetting or hydrophobic hairs that push water away or repel water. And so there's actually a micro-thin layer of air, sort of like what you see between a puck and the surface of an air hockey table. And the spider, therefore, pushes water away and doesn't punch through the surface, and so it can skate along. Well, an ant or a fly or something like that gets trapped in the surface of the water can't do that. The spider comes along and gets itself a meal that way. So it's adapted to take advantage of surface tension. Now, clearly that right there is not something that's critical for life, but there are certain ways in which that can be taken advantage of. The high surface tension of water can be taken advantage of, and it certainly is in that case, and lots of other cases like that as well. Okay. Next, let's shift gears and talk about moderation of temperature by water. This is a key feature of water that absolutely makes much of the surface of our planet livable. The thing about water is that it absorbs heat from warmer air adjacent to it, and it releases stored heat to cooler air adjacent to it. Water can absorb or release a large amount of heat with only a slight change in its temperature, all right? And the reason for that is because water has what's called a high specific heat. High specific heat. We'll define what specific heat is here in a minute, but compared to other substances, water has a very high specific heat. All right. Before we get to that, let's talk about temperature and heat a little bit. We need to define something about energy in order to understand how water does this, okay? So first of all, we have a number of different types of energy. One we're going to talk about here is kinetic energy. This is energy of motion, okay? Energy of motion. So any object that is moving through space is moving because it has kinetic energy. Now, kinetic energy is associated with thermal energy or heat. The kinetic energy associated with random motion of atoms or molecules is called thermal energy. So let's say you had a really high-powered electron microscope and you could actually zoom in and see the atoms in the table or the desk that I'm sitting at right now, for example. What you would see is that those atoms are vibrating. Okay, they're not static, they're not still, locked in place, they're vibrating. And the lower the temperature, the less they vibrate. The higher the temperature, the more they vibrate. This is called molecular motion, okay? And any substance that has a temperature higher than absolute zero, which is minus 273 degrees Celsius, has molecular motion. Molecular motion stops at minus 273 Celsius. That's called absolute zero, all right? But that temperature doesn't exist naturally on planet Earth. All temperatures are above that, so everything on Earth, or the molecules and atoms in everything on Earth, are moving due to molecular motion. So the amount of molecular motion is directly correlated with the amount of heat or the temperature of something. Temperature then is actually an indirect measure of the amount of molecular motion. You take the temperature of a glass of water, you are measuring indirectly how much those molecules of water are moving around, how much they're vibrating. Okay? Temperature is a measure of energy that represents the average kinetic energy of the molecules in a body of matter. Thermal energy in transfer from one body of matter to another is defined as heat. Okay, so you stand next to fire, for example, you feel the heat coming off that fire. That is thermal energy transfer from the fire to your body, and you feel that as heat. It warms up the molecules in you, and they start to vibrate faster through greater molecular motion, and you feel that as heat. Okay, so how do we define energy content of substances? Well, there are a number of different ways. The most common way in biology, biochemistry, and also chemistry is through the calorie. Now, everybody's heard of the calorie, okay? That's abbreviated CAL. A calorie is the amount of heat necessary to raise the temperature of 1 gram of water by 1 degree Celsius. So we're going to raise the temperature, raise temperature of 1 gram of water by 1 degree Celsius. All right. So you think about the calories on the food label. So let's say you're looking at a cup of yogurt, for example, and you see that it has 150 calories. Those calories that you see on the food label are actually kilocalories. All right, so KCAL. So a kilocalorie is actually equal to 1,000 calories. All right, so let's say that you see that there's 150 calories, actually kilocalories in a cup of yogurt. That means there's enough energy in that cup of yogurt to raise the temperature of 1 gram of water by there's enough energy in that cup of yogurt to raise the temperature of 150,000 grams of water by 1 degree Celsius. Or, another way to look at it, there's enough energy in that cup of yogurt to raise the temperature of 1 gram of water by 150,000 degrees Celsius. Okay, the water would obviously vaporize long before that, but that just gives you an idea of how much energy there actually is in our food. All right. There's another unit of energy that you sometimes see more often used in chemistry and physics, and that is the joule. You almost never see this in biology. But a joule is just another way to measure energy content, and so 1 joule equals 0.239 calories, okay? Or 1 calorie equals 4.184 joules, okay? Don't worry about the joule so much. You probably see it in chemistry, and if you take physics, you'll definitely see it there. All right, so let's get back to this idea of specific heat. So specific heat of a substance is the amount of heat that must be absorbed or lost for 1 gram of that substance to change its temperature by 1 degree Celsius. Let me say it again. The specific heat of a substance is the amount of heat that must be absorbed or lost for 1 gram of that substance to change its temperature by 1 degree Celsius. All right, so we're talking about water here, right? The specific heat of water, let's just do this, of water equals 1 calorie, all right, per gram of water per degree Celsius temperature change. This means that to change the temperature of 1 gram of water by 1 degree Celsius, you have to add 1 calorie. So, specific heat of water is 1 calorie per gram per degree Celsius. That's a relatively high specific heat compared to other substances, okay? What this means is that water resists temperature change because of its high specific heat. That means if you want to change the temperature of water, let's say you want to raise it, you have to add a really large amount of energy to change its temperature by 1 degree Celsius compared to other substances. If you want to lower its temperature by 1 degree Celsius, you have to take out a lot of energy, comparatively a lot of energy from that water to lower its temperature by 1 degree Celsius. Okay, so let's imagine that you had, let's say, two 1 liter beakers filled to 1 liter with cooking oil and water. One of them has cooking oil, one has water. You put them on a common burner, you apply the same amount of heat to them, and you want to raise their temperature. Let's say you want to raise it to 100 degrees Celsius, the point where water would boil. Well, you turn on the burner and let them heat. The oil will reach that 100 degrees Celsius threshold much faster than the water will. So the oil is going to lag. The water is going to lag behind the oil. They will both eventually reach that temperature, but it's going to take longer for water to do it. Now, let's say you leave it on the burner on long enough to get them up to 100 degrees Celsius. Then you turn it off. Well, now they're going to lose that heat, right, to the atmosphere and cool. Which one cools faster? The oil. Its temperature will drop much more rapidly back to room temperature than the water. You'll have to wait for the water to get down to that room temperature again. This is why we say that water is very good at moderating temperature. Water absorbs a large amount of heat before its temperature changes. Then once it has absorbed that heat, that water can hold on to that heat for a long time. Okay, so the water then resists changing temperature, and that means that, as we'll see in a little bit, water is very good at, say, distributing heat around the planet and making much more of the planet livable than would be the case if water had a lower specific heat. So the question is, why does water have this high specific heat? It all goes back to the hydrogen bonding that we see between the water molecules, the cohesion that I showed you before, all right? So when heat is absorbed by water, these hydrogen bonds start to break. The thing is that those hydrogen bonds are not static. They're constantly breaking and forming, and that's why liquid water changes shape or conforms to the shape of whatever kind of vessel you might put it in. We think of it as a liquid as a result. Now, heat is absorbed when those hydrogen bonds break. So as you add heat to water, the bonds begin to break more often, and then the reverse is also true. When water cools and heat is released, the hydrogen bonds form more often. So that's one aspect of why water resists temperature change. Another aspect is that the length of the hydrogen bonds change with temperature change. So as water absorbs heat and begins to heat up, the hydrogen bonds lengthen. So you can think of it this way. You put energy into water in the form of the heat. Some of that energy will go into directly raising the temperature of the water, but some of that energy is diverted away from changing temperature and instead makes the hydrogen bond length longer. So less of that heat, not 100% of that heat energy rather, is going into changing the temperature or raising the temperature. Some of it's going into making the bonds longer. It's like a thermal shock absorber, right? This is one reason why water's temperature resists changing when you add heat to it. Likewise, when water begins to cool, some of the heat comes out directly and results in a direct drop or lowering of the temperature, but some of the heat energy comes out in the form of the bonds getting shorter. So that does not contribute necessarily to temperature change. This is why water's temperature, the temperature of water does not drop as rapidly as, say, the temperature of cooking oil would, for example. So the fact that the hydrogen bonds change length is one aspect of the way that water behaves that kind of acts like a thermal shock absorber, okay? All right, so this high specific heat of water due to its hydrogen bonds minimizes temperature fluctuations to within the limits that support life here on planet Earth. Here's an example of this. So this is the Los Angeles area, right? So on any given day in the summer, for example, it can be really hot in the interior of California, in the desert areas, 106 Palm Springs, for example, 100 degrees, San Bernardino, whatever. But you go, maybe 40 miles to the coast, and Los Angeles could be 25, 30 degrees cooler. Now that's a very short distance for such a large temperature change. Why is that? It's because the Pacific Ocean right here. The Pacific Ocean in Southern California, or actually along the entire coast of California, is very cold. 68 degrees in the summer is about as high as it gets. This is why surfers and things are always wearing these 6 mil wetsuits when you see videos of people surfing out there. They're trying to avoid hypothermia. Well, that cold water acts as a thermal sink. It pulls heat out of the atmosphere over Los Angeles and lowers its temperature. Same is true of Santa Barbara up here, for example. But you go just a little bit inland, and that effect is sort of limited and finally goes away entirely, and you see what happens to air temperature over the land. This is a great example of moderating temperature. In the winter, it's exactly the opposite effect. In the winter, typically the ocean is warmer than the land, so the ocean dumps off heat over the land, and coastal areas in the winter will be warmer than areas just inland. You see that effect here in North Carolina. Here in Fayetteville, in the summer, it can be 105 degrees, but you go down to Wilmington, 100 miles as the crow flies, and it could be 10 degrees cooler because it's next to the Atlantic. In winter, it can be 45 degrees in Fayetteville and 5 or 10 degrees warmer in Wilmington. Again, because there, in that case, the Atlantic is dumping off heat over Wilmington. All right, so this is a regional effect here. But what about on a global scale? Well, take a look at this map. Now, this is a worldwide map, and it's very small scale, so it's kind of hard to see some of this, but I'm going to zoom in and show you something here. So this is the North Atlantic, and in the North Atlantic, and also in the South Atlantic, true also in the North and South Pacific, there are large ocean currents called gyres. In the Northern Hemisphere, they operate in a clockwise motion like this. So the water is doing this over very long time periods. Here at the equator, the sun is directly overhead almost all year long. So this water in the equator here is picking up lots of heat, and then this gyre is taking that heated water all the way up the east coast of the United States, just south of Greenland, Iceland, and back down toward Europe. So why is that a big deal? Well, take a look at New England. New England, is temperate. It's warm in the summer, cold in the winter, that kind of thing. Same is true along the Atlantic seaboard. But draw a line of latitude east, and you hit Spain, and even to some extent, the desert regions of Africa. Go north, and you have Ireland, Scotland, Great Britain. Here you have Norway, Finland, Sweden, for example. These areas are totally habitable. They are temperate climates, right? Draw a line of latitude west from Norway, you hit Iceland, and you hit Greenland. Greenland's not green, it's covered in ice. It's largely uninhabitable. Same latitude, Northern Europe, Greenland, habitable, not habitable. Why? It's because that gyre, which is taking all this heat, absorbing all this heat, takes that heat all the way up, and when the gyre collides with Northern Europe, that heat gets dumped off and spread over the continent. That's why much of Northern Europe is habitable, whereas due west of there you hit Greenland and Hudson Bay, which largely isn't. Very, very different environments. And the same is true in other parts of the world as well. So as a result of the water picking up that heat at the equator and holding on to it for the long term because of its high specific heat, and then dumping it off over colder regions, it warms up much of the areas of the planet and makes larger parts of the planet habitable than would be the case otherwise. Okay, very important for life on Earth. All right, so that's water's ability to moderate temperature, which is tied in with its high specific heat. Okay. Next thing is the fact that water expands upon freezing. Okay, so we know that water expands upon freezing. If you've ever taken a can of soda, Coke or Pepsi or whatever, and put it in the freezer, cool it down, but then forgot about it, left it there, you come back a couple hours later and the can is split open because the water in that can froze, and as it froze, it expanded and ruptured the can. Okay, so I bet every time in your life when you've dropped a cube of ice in water, it has floated, and rather than sink. And the reason for that is because ice expands, or water expands as it freezes. So you might not think this is a very important property of water as far as its life-giving characteristics, but it absolutely is, as we'll see. So ice floats in liquid water because hydrogen bonds in the ice are more ordered, making ice less dense than water, and you see that here in this figure. So look at liquid water. Again, the water molecules are attached to each other through cohesion, right, the hydrogen bonding. And notice that they're not very ordered, it's kind of chaotic. The water molecules are moving around, the bonds are breaking and forming constantly. Again, that's why liquid water is liquid and it flows. But as that water hits 0 degrees Celsius, those bonds lock in place and the water molecules take on this very ordered arrangement with a lot more space between them than you see here. In the ice, the water molecules are spaced out further apart than in liquid water. So let's imagine this is a liter of ice, and that's a liter of water, in which of the two do you have fewer water molecules? In the ice. And water has a specific weight. So if you have fewer water molecules in ice compared to liquid water, the same volume of liquid water, the ice will weigh less and the liquid water will weigh more, and that is why ice floats, as you see here. So this is very important for marine ecosystems, especially up by the North Pole and South Pole. You have, North Pole in particular, you have, there's no land there, it's all ice, it's all covered, the water's all covered with ice. And the reason why it doesn't freeze to the bottom is because the ice freezes on top and it forms sort of an insulating layer, almost like a blanket, that keeps the water below just a few degrees above freezing so life can persist. This is why life isn't destroyed in northern lakes when they freeze over every winter, because they just freeze over on the surface layers and the water below is kept liquid, a little bit warmer, and so the life in that lake can survive until the spring or summer. All right. So why is this important for life on Earth on a large scale? Well, we know that life began in the oceans. So if it were true that ice were more dense than water rather than less dense like it is, the oceans would have early on froze from the bottom up, and in some cases you'd have 8 or 9 or maybe even 10 miles of ice, and the sun would never have melted that. And the planet would have eventually frozen over completely, and we think life would have never formed. So this is one of those key features of water that if it were tweaked and slightly different than it actually is, life would probably never have formed in the first place. Okay, I think that's a good place to stop. In about 40 minutes or so, we'll pick up with the next property of water, which is its ability to act as a very good solvent for the second video lecture for Chapter 3.